Siddharth, to answer your question, no, batch 2 has also completed optics. Only in today's session, I will be discussing some, if they have any doubts and some questions. Topics wise, optics is completed. Okay. But yeah, batch 2 will be discussing some questions and doubts. So if RTPS 2 students have yeah, dispersion is a small topic. It's just a few minutes, 5-10 minutes. So you can join in with batch 2 to attend that, or you can run that later also. It doesn't matter. Dispersion is just a couple of definitions and couple of formulae. So you can pick that up from the video lecture, or you can attend the evening lectures first hour or so today. Yeah, chromatic aberration is to do with dispersion only. It's just a term. Okay. Don't worry about chromatic aberration and dispersion. It's a very small part. Yeah, so let's start with the understanding of waves. So what are waves as a phenomena? Okay, or what is wave motion? So any situation, now this is a general definition of waves. Okay, so it goes beyond just mechanical waves. It includes all types of waves. Okay? Any type of wave. Or any type of wave motion, or any type of wave phenomena. It is nothing but, it is when energy is propagated without any motion of particles or matter directly. So any phenomena where you can see energy is getting propagated from one point to another without any matter getting transported, or any matter moving from that point to the other point. So if from A to B we have energy which is propagating, but in such a way that no matter is actually moving from A to B directly, then such a phenomena is called a wave phenomena. Okay. So for example, you can see that you have waves on the surface of water. What is happening is, you can see that there is an up-down motion, kinetic energy. Yeah, including sound. Okay, all types of waves. This is what happens. Okay. So on the surface of water, as waves are propagating like this, what is happening is that the medium particles or the water particles are moving like this. This is the motion of the water molecules on the surface. But the energy is propagating like this. And you can see the proof of this concept. For example, you take a situation where you have on the surface of water, you have a piece of wood floating over here. And you have another piece of wood floating over here on the water surface. Now, you push this wood down a little bit and allow it to start oscillating. Okay, so it will start oscillating like this. So you have given some energy directly to this wooden piece. But you will see that because of the waves propagating, once it starts oscillating, eventually this also starts oscillating. So if you make this oscillate by giving it some energy, it will produce that wave phenomena, which will eventually make this also start oscillating. But you can see that this wooden block is not moved here. So that is giving you the evidence that particles on the surface of the liquid are not moving in this direction. It is only energy which is propagating in this direction. So immediately you realize that it's something very different from what you studied before wave mechanics. which is particle mechanics or rigid body mechanics. In anything other than wave mechanics, you'll realize that for energy to move from one point to another, physical particles have to make that physical displacement from that point to the other point. But in wave phenomena, that is not happening. Now, these are both examples of mechanical waves. Sound wave is also an example of mechanical wave. Okay? But there are many more abstract examples. On the one hand, so suppose one person wants to communicate something with another person. Now, in situation 1, what he does is he writes a letter, sends a letter. So this letter ends up reaching. In situation 2, the person A, say, he writes an email. That email reaches this person B. So in the case of situation 1, you can see over here what is happening is that information is propagated by a particle motion phenomena, or matter is transported from A to B, and that's how information and some form of energy is moving from A to B when he's sending the letter. But when he's going through email communication, and when the information is going through email communication, the information is propagated via wave phenomena. There's no actual physical particles move from A to B. So this is a more abstract example of the difference between particle phenomena and wave phenomena. So yes, there is in wave phenomena, there is motion of particles involved. If it's mechanical waves like sound waves or transverse waves on the surface of water, whatever. But the exchange of energy or the propagation of energy does not happen via the direct exchange of particles or by the direct motion of matter from one point to another. Okay, the exchange of energy happens without any matter moving from point A to point B, but at the same time energy is getting propagated or information is getting transferred. So this is a more abstract example to understand the difference between, but even this situation involves wave phenomena. Whereas this involves particle phenomena, a particle motion phenomena. It's motion of matter. Okay. So many more examples. You have seen the case of the Mexican wave in a crowd. What happens in the case of Mexican wave in a crowd? In a crowd in a stadium or something like that. It's not traditionally what we relate with, the physics definition of wave, but at the same time, it actually exactly fits the physics definition of wave. So what happens is people alternately stand and sit, okay, and you see a pattern that moves along the ground. But people are not moving along the ground. People are not moving in the direction of the pattern. So what you see in a Mexican wave is, yeah, is that's when people are cheering. Okay, so people are sitting in a crowd, and then some people stand up or jump up. Then again, people are sitting like this. Now people are alternately sitting and jumping. Okay, so you see this kind of thing. After a while, it's like this, because these people have sat down, these people are standing up. So you see that pattern. Okay, that is shifting in this direction. But the people, when they move, they are only moving in this direction. Okay. So information or energy is getting transferred without the direct motion of physical particles or the direct motion of physical matter in that particular person. Yes, okay, that kind of situation. So that's also an abstract example of waves. Okay, but yes, our everyday mechanical waves, they are the more you can say organized, not such abstract examples of transverse mechanical waves. The examples of which are vibrations on a string, or waves on the surface of a liquid. So these waves have that property in common, that in transverse waves, what happens is that the medium particles displace in a direction or along an axis perpendicular to the direction of propagation of the wave. So that is the definition of transverse waves, which is one type of mechanical wave. So for example, vibrations on a stretched string. You can see in this example what happens is, this is the shape of the string, and this pattern keeps shifting like this. So the energy propagation is happening in this direction. But the medium particles are actually going up and down in this direction. If you put a, if you put a marker on some point on the string, and as the wave is propagating through it, that point with the marker that you can see, like you made a dot with a pen or something on the string, you can see that that dot will only be oscillating in this direction along your so-called y-axis. If the propagation is happening along the x-axis, that dot will not be moving along the strings. But you can see that the energy propagation is happening along the length of the string or along your so-called x-axis. So when that kind of wave phenomena happens, that your particles of the medium are oscillating or getting displaced in the direction perpendicular to the direction of propagation of energy, then we call it which type of wave? We call it transverse mechanical wave. By definition, this is one where medium particles displace or oscillate in a direction perpendicular to the direction of propagation. Okay? And these are the two standard examples. Waves on the surface of a liquid. We discussed earlier that floating piece of wood, as waves pass through the liquid, that floating piece of wood only bobs up and down. It doesn't, if there's no undercurrent, okay, then it will not displace along the surface. It will only displace perpendicular to the surface. Okay. Whereas the energy propagation happens tangentially along the surface. So that's why again waves on the surface of a liquid are an example of what we call transverse mechanical waves. Whereas the second type of mechanical waves, they are called longitudinal mechanical waves. what happens in the case of longitudinal mechanical waves is that the medium particles are displaced during the oscillation in a direction or along an axis which is along the axis of propagation. Okay. But this doesn't mean that the medium particles are actually displacing and all the way carrying the energy with it. So, for example, we have the case of sound waves. If you do an experiment where you think about this kind of situation, you have a pipe which is open at both ends. And you have a tuning fork at this end. So as the tuning fork is sounded, it kind of vibrates back and forth like this. That causes air particles here to vibrate back and forth like this. So that pushes the air particles next to it, next to it, next to it. So you can see that the axis along which the propagation is happening, the energy is also propagating along the same axis. That propagation axis is the same direct axis along which the medium particles are oscillating, which in this case you can take as the horizontal x-axis. So this is different from the case of a string where the particles are vibrating along the y-axis, but the propagation is happening along the x-axis. So whenever this happens, that the medium particles displace in a direction along the propagation axis, we call the phenomena as longitudinal mechanical waves. So another case of understanding how sound is a longitudinal mechanical wave is something like this. You consider a point source of sound. And in three-dimensional space, it creates spherical wavefronts like this. So what is happening is that the air molecules on a wavefront, they are oscillating together like this. So their direction of oscillation is along the radial line, along the radial axis. So that radial axis is the common axis for the oscillation of the air molecules as well as the propagation of energy. Or the propagation of the wave itself. So sound is the physical model or the physical example of the second type of mechanical wave, which is longitudinal mechanical waves. So these are the two types of mechanical waves. And of course, when we are done with mechanical waves, we will see that waves are not restricted to the mechanical domain, but waves can also be in the form of electromagnetic waves. And light is an example of electromagnetic radiation or electromagnetic waves. So in the case of electromagnetic waves, what is happening is the energy that is propagating, it is not mechanical energy. Like in the case of mechanical waves, the energy we are talking about is the elastic potential energy of the medium and the kinetic energy of its medium particles. But in the case of electromagnetic waves, it is electromagnetic energy. It is in the form of energy associated with electric field and magnetic field. And therefore, no medium is required for the propagation of electromagnetic waves. But mechanical waves, it involves the transfer of mechanical energy through a medium particle, through a physical medium, okay, or a medium consisting of mechanical particles, such that the propagation of energy happens without the physical propagation of particles from one point to another. Okay. So hope the definition of the phenomena of waves is clear to all of you first of all, and then the definition of mechanical waves is clear, and further within mechanical waves the definition of transverse and longitudinal mechanical waves, that is also clear. Okay. So this is like the background kind of thing. We have to understand the difference between wave phenomena and particle phenomena. So once this conceptual aspect is clear, that what we mean by waves and what we mean particularly by mechanical waves, and further how we classify mechanical waves into transverse versus longitudinal waves. Now we are ready to start with the first section, which is going to be the proper detailed analysis of transverse mechanical waves. So this is where the first section of sound starts for us. So in this, we want to understand a very specific type of transverse mechanical wave. In fact, we want to understand a one-dimensional transverse mechanical wave. What is this? This is a mechanical wave such that propagation of energy occurs along a straight line. So the physical example of this, the physical model of this is waves propagating along a stretched string. In this, what happens is that the energy propagates along the string. So that is one dimension. Whereas the mechanical waves on the surface of a liquid, they are an example of two-dimensional transverse waves, because the energy is propagating along a surface. So it's a two-dimensional geometrical space in which the energy is propagating. But we want to start by studying the one-dimensional transverse mechanical wave. So in one-dimensional wave, what is happening? We want the energy to propagate along an axis or along one dimension, not along a surface or not along two dimensions. Okay, so therefore the physical model for this becomes waves propagating along a stretched string. So now let us develop the general mathematical equation. What is the mathematical form or equation for this? So let's try and understand that. Okay. So imagine you have something like this. You have a string which is stretched between x equal to 0 to x tending to infinity. So this is a stretched string. Now what we do is at t equal to 0, a pulse is created at x equal to 0. So by giving the string a jerk along the y-axis. Okay. This is our y-axis. So this is a string stretched from x equal to 0 to a very large distance. By infinity, we just mean that it's a very large distance. Okay. So that is the physical model of our medium. And now we are going to try and understand the mathematical form by first studying what this pattern looks like. That we created a single pulse at x equal to 0 by just giving the string a jerk. Like somebody is holding the string at the point x equal to 0 and he just gives it a jerk along the y-axis, a single jerk. So how will that phenomenon look? Let's understand. Okay, so at t equal to 0, we've given the jerk at the point x equal to 0. So we will see this kind of shape. So at a later time, this jerk would look like this. At a further later time, we're seeing that this jerk, if we imagine that there is no dissipation of energy, then we'll see that it's the same shape, but it's traveling. It's traveling like this. So this is an example of what we call, see, a traveling pulse. So this shape the pulse is observed. And we will assume that no dissipation of energy occurs because of things like wind resistance, etc., air resistance, etc. So assume no dissipation of energy. So the amplitude of the pulse, this quantity here would be the amplitude. The displacement along the y-axis remains constant with time. Okay. Now the next thing we'll understand is how to write a mathematical equation for this traveling pulse. But I just want you to first review this concept. Just go through this section once. So next up, we'll learn how to write a mathematical sort of form to represent any traveling pulse or any traveling wave. Okay. So now basically what we have to do is we have to come to a situation where we can represent something like this, a traveling pulse, or if we have a wave, then it's a series of traveling pulses, okay, which are equal in time period, etc. We'll come to those properties, but Basically, it's a series of pulses which is traveling along the axis of the string, which we'll take as our x-axis. Whereas the direction of displacement or the direction of the pulse disturbing the medium particles is along the y-axis. So how would we represent this with a mathematical equation? That is the next thing. Okay. So we want to develop the general mathematical equation of a traveling pulse and from that a traveling wave. So let's now understand this next thing. So how will we represent this thing, the general equation for a transverse one-dimensional pulse and wave? We'll understand the difference between the exact difference between a periodic wave and a single pulse also as we go along. So to understand this thing, let's first look at some mathematical aspect. Okay. So this is aside from the topic. Okay. Just for example, you know that if we have the equation y is equal to, let's say, e square minus x square. This graph looks like this. It's a parabola that looks like this. It peaks at a square at the origin and drops to 0 at plus a and minus a and becomes negative beyond that, right? Now, if I want to next do this thing for this same parabola, instead of it being like this, next I want it to be like this. I want the exact same shape, but I want this to be 1. So this point I want it to be e plus 1, and this point I want it to be minus of e plus 1. So I want this whole thing to shift by 1 unit along the x-axis. So what will this equation look like? So this is just a simple concept of transformation of graph. Can you tell me what it will look like? Yes, correct, Ganesh. So we will replace x with x minus 1. So this function now will look like so whatever was happening at x equal to 0, now that is happening at x equal to 1. Whatever was happening here at x equal to e, now it is happening when x minus 1 is equal to e. So that is a plus 1. X is equal to a plus 1. Whatever was happening at x equal to minus a, here it will happen when x minus 1 is equal to. So it is like, it's like y is equal to e square minus x prime square, where x prime is equal to x minus 1. So the x prime axis origin is at actually x equal to minus 1. Rather x equal to plus 1. Okay. So the general idea that we understand from transformation of graphs, okay, which is basically something from graph theory in maths, is that if we have the graph of any function, so let's say the graph of any particular function, it looks something like this. as a local maxima, local minima, whatever. This is the function fx. Okay. Now in the function, if I replace x with x minus a, then this graph will shift. So now this is suppose f of x minus capital A. Okay. So then the whole graph actually shifts along the positive x direction by e units. This point becomes small a plus capital A. This point becomes b plus A. And similarly, if I were to replace x with x plus a, then it would shift like this. The whole graph would shift backwards by, let's say, b units if I replace x with x plus a. So this is the idea of transformation of graphs. Just make a note of this first, this information, then we will continue forward. Okay, so this is all maths examples. We'll come to the physics part very soon. So fx getting transposed to x plus b. Okay. The graph shifts along negative x-axis by b units. Okay. And fx being transposed to f of x minus capital A here. Then graph transposes or shifts along positive x-axis by capital A. That is what we are learning from this second part here. Okay. Now the next thing you'll understand here is that in a maths function, y is equal to fx. X is basically what? X is a number. It is dimensionless. Because the argument of a function has to be dimensionless. So for example, if we write the function y is equal to x square minus 2x. Okay. So here x is just a number. So y is also just a number. Okay. Or if we write the function y is equal to sine square x. Again, x is just a number. Y is just a number. Okay. But now suppose we want to write a physics equation where x is also a position and y is also a position. Then the dimensionality of the equation has to change accordingly. Okay. So when functions are used in a physics equation, the variables are not dimensionless. So for example, when we have the equation S is equal to ut plus half at square, you can see that t is the variable which has dimension of time. So u and a are constants, okay, but they are physical constants. So u is expressed in meters per second, a is expressed in meters per second square. But if we wrote a maths equation, y is equal to 2t or 2x plus x square. Here 2 is just a number and x is a variable, but that's also just a number. So that's the difference between a physics equation and a maths equation. So for example, if we have an equation like y equal to a sine omega t. So again, you can see here that omega is a constant which is in radians per second. Okay. T is a variable but which is in seconds. Okay. Y is a variable which is in meters. Okay. So E is again a constant which would be in meters. So whether you're talking about the constants in the equation or the variables, they have physical dimensions. So accordingly, therefore, in context of one-dimensional pulse or wave, so this thing traveling along a string, so in a physics equation, what is the variable x? X is a variable that represents position along the x-axis. So x has the dimension of length. And what is y? Y is also a variable, but it represents displacement along y-axis. So again, y is also variable, but again, y is also having dimension of length. Okay. So therefore, when we write a function representing a fixed shape on the string will be represented by a function like this. Suppose this is some kind of a fixed shape. It will be y is equal to f of k into x, where k is a constant such that k's dimension is length inverse, so that the argument of the function which is kx is dimensionless. So that's the difference between a mathematical function and a physics function equation. So now, for example, if I have the equation of this particular fixed pulse, which is having its peak position at some E. Okay. This is y is f of kx, because remember x is in meters, so k is in meter inverse. Okay. Now I want to transform this to a position like this. Where this has now become E plus delta x. So this whole thing has shifted by delta x without changing its shape or size. It's the same function, but it has just got transformed along the positive x-axis by delta x. And I'll replace this function with what? I'll replace it with a function where I just replace the value of x with x minus delta x. Understood? No? Because we'll not write it as kx minus delta x. We'll write it as k the whole thing into x minus delta x. Because x as the variable of the function has to be replaced with x minus delta x for it to move along this direction. So now imagine this was traveling in such a way that this is actually equal to v delta t. Okay. So this is how the function looked at some time t. And now this is how the function is looking at time t plus delta. So what we understand here now is that if you replace a function y is equal to f of kx with a function y is equal to f of this, where v is a constant velocity, okay. V is a constant which is in meter per second, t is time in seconds, okay. And x is of course position in meters. Now what this equation now represents? This equation represents a pattern, or what we can mathematically call the graph, which is shifting along the positive x-axis such that delta x will be equal to v delta t. So it's at a uniform rate or velocity. Okay. This is what this equation now represents. Okay. This particular equation now, it represents this thing. So if at t equal to 0, your graph was looking something like this. Okay. Then at some time t equal to t, so it would have shifted by v into t. So this whole graph would have shifted by delta x equal to v into delta t, or in this case it would be vt, because this is the graph at t equal to t, and this is the graph at t equal to 0. Okay. So this represents basically, now this kind of equation represents what? It represents a traveling pattern graph. So in physics, this will now become a traveling one-dimensional transverse wave slash pulse, and it's traveling along the positive x-axis at uniform speed v. Okay, so I'll just leave you with a minute to understand this whole thing once more in detail. How we can convert a stationary function pattern like this, okay, into a traveling pattern now like this. So this kind of a function will represent a fixed shape on the stone. Okay. But replace x with x minus vt. Now in this, the moment we replace the variable x with x minus vt, it becomes a traveling shape like we've done before. This whole thing is now traveling at the rate of v. Okay, so hope the concept of this is fully clear. So now, so now next, let's actually take an example of an actual function to understand how this works. So let's do this now as a maths problem. So we have an equation given by y is equal to 5 into e raised power minus of 2x minus 60 whole square. So this is given that y is displacement along the y-axis in millimeters, and x is the position of a point on the x-axis, and x is expressed in meters, and t is time expressed in seconds. Okay. So what we'll do is plot y versus x at t equal to 0. Plot y versus x at t equal to 1 second. Plot y versus x at t equal to 5 seconds. Find the amplitude that is maximum displacement along y-axis and velocity of the above traveling pulse. So when you plot the graph, you'll understand why we are calling it a traveling pulse. And from the graph itself, you will be able to tell the answer to the third part. Okay, so try this out, people. Yes, that's correct, Ganesh. Correct, Siddharth. Somadeep, correct. So let's start by plotting the graph at t equal to 0. Y will become 5e raised power minus 4x square. Because in this function, we just replace t as 0. So it will become 2x whole square, but the minus sign is outside. So the graph of this function, you'll observe, will look something like this. This e raised power minus 4x square term, it is first of all an even function. Okay. And it has maximum equal to 1 at x equal to 0 and minima equal to and tending to 0 as x tends to plus minus infinity. So basically like e raised power x is a graph that goes like this. So e raised power minus x is a graph that goes like this. So e raised power minus of mod x would be a graph that goes like this. So e raised power minus of x square. The graph that would have a curve here, whereas this would have a sharp corner. Okay. So this is the graph theory sort of understanding of this, how it happens. So coming back here, this would look like this. So y is in millimeters, x is in meters, and this would be 5. So now if we compare this with what is happening at t equal to 1 seconds, it would become e raised power minus of 2x minus 6 whole square. So that is, you can see that you have replaced x with x minus 3. So this whole graph has shifted something like this, let's say, where the peak point is at x equal to 3 at t equal to 1 second. This is where the peak was at t equal to 0. Yes, so that is what we will see, that x and t has to be always linear. Okay. It's traveling with the speed. Okay. Now likewise, at t equal to, how much was it, 5 seconds. Yeah, 5 seconds. You can see a is 5 actually. So or we can write this as so you can see that this pulse has traveled to some kind of a position like this. It's x equal to 15 at t equal to 5 seconds. So just from the graph itself, without doing too much mathematical analysis further, you can see that therefore y is maximum value, which is the amplitude, is equal to 5 millimeters, and the wave speed or the pulse speed is 3 meters per second. Okay. So you can see that it represents the function, represents a pulse traveling along the positive x-axis at v equal to 3 meters per second. Okay. And with an amplitude equal to this much. Okay, so this is one demonstration of how we can represent the equation. In fact, this kind of equation is called the exponential pulse. So this form is called the exponential pulse. this is the equation of a transverse exponential pulse. Amplitude equal to capital A and velocity equal to minus or plus of V. Now, what this minus plus means that if it is k of x plus Vt, then it represents a pulse traveling along negative x-axis at speed, whereas if it is k of x minus Vt, that represents a pulse traveling along positive x-axis at the speed v. So in general, for the general equation, we can include both the cases. It could be traveling along the negative x-axis, it could be traveling along the positive x-axis. So this sort of equation is called the general equation of an exponential traveling pulse, because we use the exponential function to represent it. So here, understand that E, K, and V are constants. Yes. Y is a function of X and T, where these are the variables. So अगर ये x plus vt होता है, so see what is happening. We have a function like this. And what is happening at t equal to 0? Okay, it's this. At t equal to delta t, it is okay. So it is going from this to something like this now. So this travels in which direction? Negative direction. Okay, so whatever this was at t equal to t, now at t equal to t plus delta t, it will travel in this direction. Okay. So that is what happens if I replace x with x plus vt. It becomes a function traveling along the negative x direction. So this is traveling along negative x axis at the speed. Okay. Is it clear now? Yeah, Sudhir, is it clear? So the algebraic sign अगर plus है दोनों के बीच, then it is traveling along the negative x direction. और अगर minus है x minus vt, then it is traveling along the positive x direction. Okay, good. Okay, next, let's look at another example to understand another set of properties. Okay. So these examples are not arbitrary, they actually have proper physical significance. Now we have something like this. Let us say this is 4 sine square pi by 10x minus pi by 4 p. Okay. So in this, y is transverse displacement in millimeters. X is position on the x-axis in meters, and t is time in seconds. So you can see that quantity pi by 10 is actually pi by 10 radians per meter, because the quantity inside the bracket has to be dimensionless. That quantity pi by 4 is pi by 4 in radians per second, and the quantity 4 is 4 millimeters. So these are all the constants in the equation, but they are physical constants. So anyway, now what we want to do in this is to plot y versus x at t equal to 0, t equal to 1 second, t equal to 2 seconds, t equal to 3 seconds, t equal to 4 seconds. Find the amplitude and the speed of propagation. You have to be careful about the amplitude. We will discuss. Yeah, correct. Uh, so if you look at the graphs, you understand a lot of this in detail. Let's start by understanding the graph at p equal to 0. Y becomes 4 sine square pi by 10x. So that graph looks like, let's say it looks, let's say it looks something like this. So it varies between 0 and 4, and it reaches the peak value at 5, then again reaches 0 at x equal to 10, then at 15, then 20. This is what the graph is looking at t equal to 0. Now if we compare this with the graph at t equal to 1 second, you'll see minus pi by 4. So this time you'll see the graph is such that this is the peak value, and it's become like this. At 0 it is actually 2, and this point is where this has become pi. So it is 2.5. This point is where this thing has become pi by 2. So it will become pi by 10x minus pi by 4 is equal to pi by 2. So pi by 10x is 3 pi by 4. So x is 7.5. Similarly, this point will become 12.5. Similarly, this point will become 17.5. Like that. Similarly, if you now see at t equal to 2 seconds, and the function will become this. So it will become effectively the cos square pi by 10x function. So that thing in comparison looks like this. Similarly, if you look at the function at t equal to 3 seconds, again you will see it's become this type of function. Again 2.5, again 7.5. And at t equal to 4, you'll see it's back to the original sine square function. Because sine square function has a periodicity of pi, so it's back to the first one. So now you can see that if we superimpose all these plots, we get something very interesting. So let me see if I can draw a reasonably accurate kind of graph. A little bit challenging on this medium. So at t equal to 0, it's the sine square function. So this is what it is looking like at t equal to 0, where this point was 5, this was 10. So now compare this with t equal to 1 second, and it's become like this. You can see that this is all shifted by 2.5 meters. Then compare this with before that was t equal to 1 second. Then compare this with t equal to 3 seconds or 2 seconds rather. So 2 seconds में क्या हो रहा है? Becoming that cos square function. So it's like this. then it's back to this position, this one, at t equal to 3 seconds, and then back to this original black one at t equal to 4 seconds. Okay. But actually all the time the wave is traveling. So in this next thing you can see it is traveling another 2.5 meters. Then it's traveling another 2.5 meters. Then finally it's traveling 5 meters. Oh, sorry. At 3 seconds, it will look different. At 3 seconds, it will look like a different graph. It looks something like this. Because if I go back to another 2.5 meters and then finally it's moved another 2.5 meters. So this graph actually looks different. This is not this. This graph will look like this. You can see at 2.5, this will become uh, 1 by 4 minus 3 by 4. So it will become minus half. So it will reach the peak. Okay. Whereas at 5, it will become pi by 2 minus 3 pi by 4. Okay, so it will reach 0. Right. So now the interesting thing is that you can see here that your particles are oscillating between 0 and 4 only. So that's the important thing to understand here, that look at the graph carefully. The medium particles are oscillating along the y-axis between between y equal to 0 and y equal to 4 at a time period of capital T equal to 4 seconds. So for example, if you just observe the particle at x equal to 0 in the above graph, the particle at x equal to 0, its y coordinate was initially how much? 0 at time t equal to 0. Just give me a moment, people. I reshare the screen. Just have to restart that program. Starts giving errors. It's too much of data on the clipboard. Can't handle. Just a moment. Yeah. So now keep context of the graph. Okay, so you can see that जो particle origin पे था x equal to 0 पे, what is its position at t equal to 0? It's where the black line is. Okay, so it's at y equal to 0 at t equal to 0. Okay, then it is at y equal to plus 2 at t equal to 1 second. That's where the blue line goes. Okay, so the particle goes from here to where the blue line is. Okay, because the shape of the string is shifted like that. You know? So in the original shape of the string, which was the sine square wala graph, the black colored graph, this particle was at 0. But by the time the shape of the string is shifted to the blue colored graph, this particle has gone from 0 to 2. Okay. Then similarly it's gone from 2 to 4 in your time 1 to 2 seconds. Then it is back to plus 2 at t equal to 3 seconds. And finally it is back to 0 at t equal to 4 seconds. So one complete oscillation is done for that particle. So that particle is going from 0 to 4 and back in 4 seconds. Okay. But if you compare this with the particle which is at, let's say, 2.5, तो particle x equal to 2.5 पे वो initially कहाँ पे था? 2 पे था. Then from 2 it has gone to 0. Then it has come back to 2. Then it has gone to 4, the green colored graph, and then it has come back to 2. Okay, so if you compare this with, whereas the particle at x equal to 2.5, this particle was at y equal to 2 at t equal to 0. Then it came down to y equal to 0 at t equal to 1. Yes, exactly, Suti. That's what's happening. Then it came back to y equal to 2 at t equal to 2 seconds. Then it went to y equal to 4 at t equal to 3 seconds. And then it's back to y equal to 2 at t equal to 4 seconds. You can see that it completes one oscillation. Here it is completed one cycle or one oscillation. But you can see that these two particles, they are both oscillating with time period equal to 4 seconds. Okay. Between 0 and 4, between y equal to 0 and 4, but with different phase. Okay. But with phase difference. They are not oscillating in phase. Similarly, if you see the next particle, the particle which was located at x equal to 5, ये कहाँ से start कर रहा है? It is starting from 4. It's coming down to 0, then sorry, from 4 to 2, then to 0, then back to 2, then back to 4. Similarly, you see the particle at x equal to 5. Okay. It is at y equal to plus 4 at t equal to 0. Then y equal to plus 2 at t equal to 1. Then coming down to 0 at t equal to 2. Then going to 2 again at t equal to 3. Okay. And finally coming back to plus 4 at t equal to 4. So it's completed one cycle. So like this, you can see that all medium particles continuously oscillate. Okay. Between y equal to 0 and y equal to 4 millimeters at time period 4 seconds. Okay. So because this is the case, as far as oscillation is concerned, okay, the definition of amplitude will become something slightly different here. The mean position is y equal to plus 2, okay, and the extreme positions are y equal to 0 to y equal to plus 4. So according to definition of oscillations, okay, so therefore particles oscillate with amplitude two millimeters. So the amplitude will be 2 millimeters and time period equal to 4 seconds. In fact, they are in SHM because that sine square function can be reduced to a sine function also. So first of all, people, I want you to thoroughly understand these graphs. I want you to thoroughly understand. So let's go back to the question. So this was, so you can see that this can be reduced to the form y is equal to 4 sine square k of x minus dt, okay, where k is pi by 10 and v will become pi by 4 divided by pi by 10. Okay. This is radians per second divided by radians per meter. So v will become 2.5 meters per second along the positive x-axis. You can see that here y is a function of k into x minus dt. This kind of thing. But that function is which function? That function is the sine square function. Where this function is the sine square function. So it's a periodic function. Unlike the previous case where it was exponential function, non-periodic. So therefore, y represents a wave. Instead of a single pulse, it represents a continuous wave. So additionally, there is a property of time period also. for the medium particles, okay, which we'll also understand in terms of wavelength later. Okay. So just first make sure you're clear with this analysis, that when you recognize the function, you can see it's this type of function. So it's falling in the category of general equation of traveling wave. Yes, so Suthit, to answer your question, when we talk about a continuous wave, it is a continuous series of pulses which is at the uniform rate. So the medium particles are oscillating. Whereas when we talk about a single traveling pulse, the medium particles are not oscillating, they're having a one-time motion. Like in that exponential pulse we saw earlier, the medium particles went from 0 to amplitude and then came back down to 0 and then remained fixed. Whereas in this sine square function, you can see the medium particles are continuously oscillating. Whatever the shape we saw changing between 1 and 4 seconds, between 4 and 8 again it will change exactly the same way. Then between 8 and 12 it will exactly change the same way. So the medium particles are continuously oscillating. So next let us look at the graph part. So this was the graph at t equal to 0. It looked like this. So it's a sine square function. Then at t equal to 1 second, it's still a sine square function, but it's transformed. So it's become like this. So the shape has changed from this to this. Further 2 seconds, it's further shifted. It's become like this. 3 seconds, it's further shifted. So now if we superimpose all the shapes in the same graph, so you can see that the medium particle which was present at x equal to 0, initially at t equal to 0 it was here. Then 2 seconds में यहाँ गया, then 4 seconds में यहाँ गया, then वापस 2 seconds में यहाँ, sorry, 0, 1 second, 2 seconds, then 3 seconds, then 4 seconds. Whereas the medium particle at 2.5, it was here at t equal to 0. So it went from here to 1 second here, then 2 seconds back here, then 3 seconds here, then 4 seconds here. And the medium particle at 5, at t equal to 0, it was at plus 4. At 1 second, it came down to 2. 2 seconds, it came down to 0. Then 3 seconds back here, then 4 seconds back here. Okay. So the shape of the string you can see is continuously changing like this. It's going from this kind of shape. A moment later, it is this kind of shape. A moment later, it is this kind of shape. So the medium particles are continuously doing this, going up and down, continuously going up and down. The medium particles are not moving like this. It's the wave which is moving like this. This is the propagation direction of the wave, but the medium particles are oscillating like this. Because it's an oscillation now, it's not a one-time motion. So it is called a continuous wave, or in short, just a wave. Okay, so now putting together all this information that we've learned so far, you can see that this type of function that we write, the amplitude will be 2 millimeters. I have explained here why the amplitude there is 2 millimeters. Just back to this. Yes, so any traveling function now represents a wave phenomenon. Okay, then understood now. So the amplitude will be 2 millimeters, not 4 millimeters. Okay. Now this sort of function we can write it like this. Omega t. I just introduce a new variable where omega is k into v, or v is equal to omega by k, such that omega is a constant having dimensions of time inverse, k is a constant having dimension of length inverse. Okay. So instead of writing it as k, the whole thing into x plus minus vt, just write it as kx plus minus omega t. So this thing it represents, mathematically it represents a traveling pattern or shape with a velocity of minus or plus omega by k along the x-axis. So now we call this the general equation of a transverse one-dimensional wave motion. This becomes the general equation. But further, in this general equation, if the function f is a periodic function, okay, like that example of sine square function, or the example of sine function, or cos function, or anything like this, then this thing represents a one-dimensional periodic wave or continuous wave. Transverse, of course. Whereas if the function is non-periodic, example the exponential pulse, then this thing represents a 1D traveling pulse with transverse displacement. So in a periodic wave, the medium particles oscillate with a definite amplitude E and time period T. Whereas in traveling pulse, the medium particles do not oscillate. They have a one-time motion kind of thing. Okay, so this is the further classification of your traveling phenomena or your wave phenomena into these two categories: periodic wave or continuous wave versus non-periodic pulse or traveling pulse. No, the energy is propagating along an axis beta, so it is not two-dimensional. Understanding the point? The graph is y versus x, that's okay, because that's the transverse displacement for the different positions at a given time. Okay. But the propagation of energy is happening only along the x-axis. So it's a one-dimensional wave. A two-dimensional wave would be the waves on the surface of a liquid, okay, where you would see that you could write the displacement along the z-axis, whereas the position of any particle is on the horizontal xy plane. Understood, Sudhir? Yes, propagation of energy is happening along one axis here. So that was the definition of one-dimensional wave. So in this one-dimensional wave equation, you can see that this pattern, or it's traveling along the x-axis. So this is the propagation of energy that is happening along one dimension, whereas y is the transverse displacement of a medium particle x equal to x at time t equal to. So that's why y is a function of x and t. Okay, so hope these points are clear. And as we discuss more and more examples and we get into the mathematics of it more, you will get more clarity about this. Okay, but this is so far about the the classification of transverse moving shapes into two categories: continuous waves versus pulses. Okay. Also, one more thing here is that this function it can be interpreted in two ways. The interpretation of the function, we can fix the value of time. Okay. So if we fix the value of time, then what is happening is, suppose at t equal to t naught, what is happening? Y is now becoming a function of x. Okay. Y at t equal to t naught is f of kx minus omega t naught plus minus. Now this thing is now become a constant because we fix the value of t. Okay. So what does this represent now? So this now represents in the original equation of the wave, which was kx plus minus omega t, मैंने t के value को fix कर दिया है. So क्या हो रहा है? I'm getting y as a function of x. T is no longer a variable in the equation. So I'm getting y as a function of x. So what does this now represent? This represents what we call the snapshot, like a photograph of the medium's shape. Its shape at the instant t equal to t. So for example, we had that equation 4 sine square pi by 10 x minus pi by 4 t. इसमें जब मैंने t के वैल्यू को कुछ सब्स्टिट्यूट किया, फॉर एग्जांपल वी सॉ t equal to 3 seconds, this became 4 sine square pi by 10 x minus 3 pi by 4. So this thing now represents what? It represents the snapshot of the medium at the instant t equal to 3 seconds. And that was this graph. Some graph like this, suppose. So it was a y versus x graph at a fixed value of t equal to 3 seconds. So that is one way of interpreting this function. Okay. Because we cannot plot three-dimensional graph. We have to plot the graph in a two-dimensional diagram. So y is now a function of x and t. So we have the option of either fixing the value of time and looking at y as a function of x, in which case what we're doing, we're looking at the shape of the medium at that instant. So it's a snapshot picture, like a photograph or an image of the medium at that particular instant of time. On the other hand, we can also do another thing. If we fix the value of x, so x equal to x naught. So what is happening? We are looking at a single particle in the medium. इसका लोकेशन क्या है? उसका लोकेशन या उसका एड्रेस है x naught. Okay. And we are looking at its displacement as a function of time. We fix the value of x. So we are looking at its. So we're looking at the displacement, the transverse displacement of that particle, that particular particle, this location x equal to x naught as a function of time. for example, again I have this particular wave equation. Like this. Okay. Now suppose I ask that describe the motion of the particle at x equal to 10 meters as a function of time. So what I'll do is, in this I will substitute the value of x as 10 meters. So I'll substitute x equal to 10. So that will become 4 sine square pi minus pi by 4t. So that will become equivalent to 4 sine square pi by 4t. So this now, if I were to plot this, this would represent what? It would represent y as a function of time for that particular particle. So I would see that as a I would see that the particle at x equal to 10 meters oscillates between y equal to 0 to y equal to 4 millimeters with a time period of 4 seconds and an amplitude of 2 millimeters, because the mean position is okay. So these are two separate ways of interpreting the wave equation. In one case, you fix the value of time, so you're looking at the snapshot of the medium at that particular instant of time. In the other case, you fix the value of x, so you're looking at a particular medium particle's motion as a function of time. So in this case, you're plotting y versus time. Y becomes a function of time for that particular particle. In this case, you're plotting y as a function of x at that particular instant. So that's why this is a snapshot picture, whereas this is the general displacement of that particular particle as a function of time. Okay, people. So this is all about the general equation of transverse one-dimensional waves, both in the case of traveling pulse as well as in the case of continuous waves. Now, next time onwards, we will start looking more carefully at the standard harmonic wave, which is nothing but when the function is the sine function or the sinusoidal function. So just like I've used sine square function over here, if I replace the sine square function with the sine function, so the general equation is of this type: y equal to a sine kx plus minus omega t plus some phase constant can also be added. Okay. This is the general equation of what we call a harmonic or sinusoidal wave. So that is the more standard type of wave, and all other waves can be constructed by superposition of these. So next time onwards, we'll be looking at this in more detail, and most of our definitions and mathematical analysis will be based on this. But in addition to this, you should also know the general form. So your sine function can always be replaced with any other periodic function, or even with a non-periodic function like the exponential pulse that we studied. Okay. So just do a revision of the lecture notes from today, because conceptually this part is very important. And there are few questions from H.C. Verma which you can start working out, which I will list out for you and send you as the homework. And I don't think you have received the module for waves yet. Have you got the PDF of the module? Okay, so I'll find out. If not, I will get the module sent to you. So, actually, you have got the module, so you can start reading from the module also. Okay. And in this particular chapter, it will also help if you read some in-depth theory from Resnick Halliday, etc. Okay, so some good textbook like Resnick Halliday would be ideal for the theory reading part, because it's quite a conceptual chapter, the entire mechanical waves part. Okay. So you can start with reading from the first chapter of Resnick Halliday. Okay. Actually, group 2 doesn't have it, so I'll send the module to group 2. Okay, and you can start with few questions from H.C. Verma, which I will list out for you. H.C. Verma has waves in the first book, Concepts of Physics Part 1. So that again has 2 chapters. The first one is waves on a string. So you'll see the first part of the chapter is in fact about this general equation of traveling wave and things like that. You can go through that also. Okay, so that's it for today's class, people. Now, students of the RTPS 2 group here, if you like, you can join today's evening batch, especially if you have some doubts in optics, geometrical optics. If you worked out questions and some doubts are pending, because today's lecture in the evening is mostly for doubts. I will take about 20-25 minutes to discuss about the dispersion of light through a prism and a couple of formulae related in that, so that you can complete there. And if for some reason you're not able to attend today evening's lecture, then just let me know and I can cover that with you separately. I can send you the video link also and send you some questions. You can do it that way also, or maybe someday we can extend the lecture and cover that portion again. But really that is not something which is very critical. The more important thing is, now that optics is finished, you clear all your doubts. So if your doubts are ready and you have the time in the evening, you can join the 6 o'clock lecture for covering those doubts. And if not, then just send me the doubts at a later time and I'll help you out with that. Okay. So that's it for today's class, people. And all the best and stay safe.